Next up on the list is histidine. Histidine is aromatic and also cation, and I'll show that later. At cellular pH of around 7.4, you'd expect roughly 10% of histidine to be positive and the rest to be neutral. And once it is positive, it's going to be hydrophilic. So the hydropathy index here is negative 3.2, which is very hydrophilic, but that might just apply to the positively charged histidine. I think that's what makes histidine so special, is that in a protein, it can change its characteristics based on the environment that it's in. As the protein moves into a more acidic environment, you can get more positively charged histidines. Just the ratio will increase as there's more free hydrogen ions to bind to the histidine. All right, so I'll draw it here, alpha carbon carboxyl group on the side here. And amine group on the side here. So histidine will have a carbon kind of separating the aromatic part of the side chain from the protein backbone. So you have basically alternating carbon-nitrogen, kind of a ring here. And then you need some double bonds. I'm not sure. Well, you need to have them in a way that you leave one of the nitrogens without a double bond. And this probably has resonance, so there's not going to be necessarily I can't say for sure, but there might not be necessarily one nitrogen with a hydrogen. It might be more just kind of smoothed out with the hydrogen. I don't know, drifting around. So when it does become positively charged, there'll be a hydrogen that sticks to this nitrogen here that has the double bond. So maybe the resonance isn't actually a thing with this molecule. So here's how they drew it. Here's the alpha carbon and the side chain. And you can see it over here. So here's the N terminus and the C terminus. And then you have this aromatic side chain that can become positively charged. So you can see here in the positively charged amino acids, and at cellular pH of around 7.4, you can see that the other positively charged amino acids have a number well above 7.4, and histidine is below 7.4. And that's going to mean that the majority of histidine is not charged. And you can see on this page here, they're showing different pHs of the solution that histidine is in, and it's a little fuzzy, but you can see at more acidic environments you have a positive charge on the side chain, on the nitrogen that has the double bond to it. And then at more basic environments, that nitrogen will be showing kind of like the free electrons there. But the side chain will be neutral in these environments. So histidine, HIS, for the symbols, 2 codons. It is essential, so it needs to be included in your diet. Histidine can be modified to become histamine. And if you ever have taken antihistamine, an antihistamine blocks histamine molecules as part of your immune response and your allergies. So you should be somewhat familiar with at least the term histamine. But you can see here histidine being converted into histamine by removing this carboxyl side chain on the I call it the protein backbone, but the main carboxyl group on the amino acid, and that gets released as CO2 because there's a carbon, 2 oxygens, and the hydrogen gets left behind in the cytoplasm. Actually, maybe the hydrogen gets attached here in the histamine molecule. So histamine was named first, and then histidine is named after histamine. So histamine means tissue amine. So with the positive charge, well, actually, without the positive charge, you have this negative electron pair. Well, it's not negatively charged, but there's a slight polarization, I guess. And so with the zinc finger motif, I guess you call it, but the positive zinc ion is going to be attracted to the slightly negative charge on the histidine. Histidine and the cysteine side chains that are surrounding the zinc ion here. So the pKa we saw was 6 for histidine, and I think this should apply to the situation, even though I don't think of histidine as an acid on the side chain. But you have in a pH of 7.4, a pKa of 6. It will determine the ratio of neutral histidine, and then HA is histidine with a hydrogen ion attached. So the HA is the positively charged histidine. And I wrote a Python script just to do the computation there. So here's the original equation: pH equals pKa log base 10 of A over HA. And that gives you a ratio of A to HA of around 25. And then using that equation, that ratio, plus having the concentrations add to 1, so that we're dealing with percentages, it comes out to, using this math here, your positively charged histidine is around 3.8%, and the neutrally charged histidine is about 96.2%, which are different numbers than they give here. So maybe my math is wrong, or my assumption that this is a valid equation for the situation is wrong, but it's in the ballpark of 10% positive, 90% neutral. And as I mentioned, this allows a protein to become positively charged in certain environments and be neutral on those specific amino acids in a different environment. So it kind of allows a protein to recognize where it's at and change its like a conformational change.